This meeting is being recorded.
Very good afternoon, all of you. Am I audible?
Yes, sir.
Okay. Okay. Screen is visible.
Yes, sir.
Okay. Now, in last lecture, we have discussed about the second order effects of CMOS transistor, right? Or you can say it's a MOS transistor. Till now, we haven't discussed about the CMOS transistor that we are going to discuss now. Okay. So now today's topic of discussion is technology scaling. Okay. Now, as you know, day by day, we are moving towards the nanotechnology, right? So what is aim of this technology scaling, or what is motto behind this technology scaling, is to reduce the size of chip, right? To reduce the size of chip means whatever the uh, different ICs, different SO system on chip are there, right? So what is the aim of this technology scaling is to reduce the size of chip, right? So that on a very small area, the maximum number of transistors or maximum number of gates can be occupied, right? And what is use of this? See, when you reduce the size of chip, right? When you reduce the size of chip, on the material required will be also less, and there are certain many more advantages of reducing the chip size. Okay, now the question is how to reduce that, right? The question is how to reduce that, and this technology or this aspect of technology is known as technology scaling, right? So basically this technology scaling has a threefold objectives, right? It has a threefold objective. That means they are interlinked with each other. They are kind of interlinked with each other. So what are these threefold objective of this technology scaling? Increase the transistor density, as I told you, on a very small space, maximum number of transistors should occupy, or we are trying to make it occupy. This is the first objective. Second, reduce the gate delay, as on a small area there are increased density of transistors, transistor, but obvious is the distance between two transistor is also distance between two transistor is also less, so that the gate delay, that means what, the signal or the time taken from one gate, right, to send the signal or to pass the signal to the other gate, it should be minimum, right? And the third objective is reduce the power consumption, right? So what are the three-fold objective of this technology uh, scaling? First one is the increase the transistor density, increase the transistor density. Second one is the reduce the gate delay, and third one is the reduce the power consumption, right? Now at present, between two technology generation, the objectives are doubling the transistor density, reducing the gate delay by 30%, right? And 40% increasing frequency, reducing the power by 50%, right? That means power should require to reduce to the 50%, gate delay should reduce to 30%, and the number of increasing transistor density means, but how much we supposed to increase? So we need to double its density, means for a particular area chip, if the previous technology, with the help of previous technology, only 100 transistor, its capacity to occupy only 100 transistor, now it should occupy 200 transistor. It should be doubled, right? And as you know about Moore's law, what Moore's law tells us, after every 2 years the number of transistors, right, that the capacity of transistor to occupy on a chip get doubles in every 2 years. That Moore's law, right? And whatever the technology flow, or whatever the consequences, right, that are happened in the technological progress, and we are still now, we are actually witnessing that the uh, chip size is getting reduced. We are moving towards the nanotechnology, right? All that things we are experiencing now. So this is what the technology scaling. Now how it is achieved, right? So we have now seen the objectives of technology scaling. First, why we should go for technology scaling? So there are certain objectives, right? Main three objectives: to increase the transistor density, to reduce the gate delay, and to reduce the power consumption. So how to achieve these three objectives, right? How to achieve these three objectives? So first, all the device dimensions are reduced by 1 by alpha. You can do that, right? Second, concentration densities are increased by alpha. Device voltages should reduced by 1 by alpha. And the that 1 by alpha is typically a 30% reduction in the dimension. That means if 1 by if you take 1 by 30, so approximately it will come 0.7. Okay, so this is how you can achieve. That means what? You can reduce the size of transistor, you can reduce, or you can actually uh, uh, reduce the supply voltage level, right? If you require 5 volt, you can go for 3 volt or 2 volt or 1.2 volt, like that. So this is how you can achieve this scaling. Now but in a practical ground, what parameters that we supposed to change so that all these objectives are achieved, right? In a practical scenario, what are different parameters that we should manipulate, or that we should redefine, so that we can able to achieve the objectives of this technology scaling? So first one is a supply voltage, that is VDD. It should be reduced by alpha. Second is a gate length L, that should be also scaled by alpha. Gate width, that is W, that should be also scaled by alpha. Then gate oxide thickness, that should be scaled by alpha. T ox, that is gate oxide thickness. Junction depth xj, that also should be scaled by alpha. And substrate doping, that is Na, that should be also multiplied by alpha, right? Now these are the scaling variables. Means what? Okay, we have seen the objectives of technology scaling, right? We have seen the methods, but how to inculcate that methods, right? Actually, when we are dealing with the MOS device, okay, so how we are actually uh, how we are actually achieving that? So these are the some scaling variables, right, that we should change, or we should manipulate to achieve all these objectives. Okay, what are these variables of the MOS device? Supply voltage VDD, that you know, that you can reduce. Gate length, that you know, that you can reduce. Gate width, that you know, that you can reduce. Gate oxide thickness Tox, that you can reduce. Junction depth Xj, that you can reduce. Substrate doping, that you can multiply, right? So by changing these many parameters or these many variables of that particular MOS transistor, you can actually scale that device to some lower level, right? Now this is the scaling variable, and this is called as the constant field scaling, right? By changing this parameter, whatever you are going to achieve is called as constant field scaling, because the electrical field across the gate oxide does not change when the technology is scaled, right? Now, if the power supply voltage is maintained constant, the scaling is called as constant voltage. That means now this supply voltage VDD, if you are if you are not going to change that, then it is called as constant voltage scaling, right? Now, in this case, the electric field across gate voltage increases as technology is scaled down. As technology is scaled down. So basically there are two types. By changing this variable, it is a constant field. That means whatever the gate oxide or the voltage across gate oxide, that does not change, right? But if you keep the voltage constant, right, then the field, electric field, nothing but voltage across gate oxide region is increases as technology is scaled down. So but what is the best method out of this constant field and constant voltage? So due to the gate oxide breakdown below zero point 0.8 microampere, only constant field scaling is used, right? That means what? You have to reduce or you have to scale this all parameters, right? So that the electric field across the gate oxide does not change. So in a practical scenario, this constant field scaling is always used. Okay. Now, what about the interconnect scaling? Okay, fine. We have this is for the one device or the one particular MOS transistor. You have scaled down. But what happens if there are n number of MOS transistors, those who are connected in series or maybe a parallel? So this type of it is called as interconnect scaling. Okay, so these higher densities are only possible if interconnects are also scaled, right? That means what? Whatever the if you have two MOS transistors, so you have scaled down the MOS transistors. Okay, but what about the interconnecting wires or the interconnecting paths that actually connect these two MOS transistors? You have to scale down that also, right? म्हणजे एक उदाहरण द्यायचं सांगितलं की थोडक्यात तुम्ही जर का शर्ट जर का तुम्ही लहान केलात तर पॅन्ट पण लहान करावी लागणार ना, बरोबर आहे का नाही? तसं तुम्ही मॉस ट्रान्झिस्टर जर का स्केल्ड डाउन केले तर इन दॅट रिगार्ड द इंटरकनेक्टिंग पाथ also you have to scale down, right? So it is all about the scaling. So that aspect is called as interconnect scaling. So higher densities are only possible if the interconnects are also scaled. Now how to do that? Reduced width, that increases the resistance. Denser interconnects, that means higher capacitance. To account for increased parasites and integration complexity, more interconnection layers are added. That means what? To if you scale these interconnects, but there are certain drawbacks. What are these drawbacks? It will increase the resistance, it will increase the parasitic capacitance as well as the integrated integration complexity. So when you scale down the interconnects, right, it will get scaled down, but with certain disadvantages. What are that? Resistance will get increased, right? Why resistance will get increased? What is equation of resistance? Rho into L by A. So if you, this rho means resistivity, right? Resistance is equal to rho into L by A. L is the length of cross length and A is the area of cross section. So if you reduce the area of cross section, the R is going to increase, resistance is going to increase. That means what? By scaling down the interconnects, it will increase the resistance, it will increase the parasitic capacitances, right? MOS transistor has certain extrinsic and intrinsic type capacitances, so it will also get increased. So how to scale actually now the interconnects? So the solution is you can add more interconnect layers, right? so that these problems cannot can be addressed properly, and there will be a proper solution to these problems of scaling interconnects, right? Thinner and tighter layers, that are local interconnections, and thicker and sparser layers, that are global interconnections and powers, right? So if you use two different layers for the interconnection, these uh, problems of these problems, or the we can say these are the what are the drawbacks of interconnect scaling, can be reduced or can be avoided, right? So this is about the interconnect scaling. So this is a total scenario of what are the scaling variables, right? Then device repercussion and circuit repercussion. So what are the different variables? We are talking about the constant field scaling, right? Supply voltage, channel length, channel width, gate oxide thickness, junction depth, and substrate doping, right? Now with this uh, parameters, when you scale down, right, device will get scaled down by alpha. Now what is device repercussion? Electric field across gate oxide, depletion layer thickness, that means these are the what we can say the fixed areas. Then gate areas, gate capacitance, drain current, and transconductance, right? Now circuit repercussion, gate delay, current density, DC and dynamic power dissipation, power density, and power delay product, these are also going to scale down. Okay, so this is about the technology scaling. Now next point of our discussion is a CMOS inverter, right? So now we have studied about the MOS transistor. Okay, now you have clear with the MOS transistor, NMOS and PMOS. Now what is CMOS inverter? So as you know, NMOS is known as normally off, बरोबर है कि नहीं? NMOS is known as normally off transistor, and PMOS is known as normally on transistor. Now, when the gate is logically zero, right? For NMOS transistor, when it is called as normally off, the gate is logically zero. And for a PMOS, while it is called as normally on transistor, that means what? Gate is logical 1, right? Now, when you study the NMOS and PMOS carefully, there is one very fantastic observation, right? There is one fantastic observation for the NMOS. When you apply a certain gate voltage, right, for a NMOS transistor, when you apply certain gate voltage, that means this high voltage, it will get short circuited, right? It will get short circuited, and it will pass the input towards the output. Now, when you don't apply anything, right, towards the gate, it will act as an open circuit, right? And it will not pass anything, that means ID will be 0. Now in that case, this is a off switch. In this case, when you apply certain high voltage beyond threshold voltage, it is act as a on switch, right? Now NMOS transistor have certain advantage that it can pass good logic 0, right? Means what? In between these two conditions, this off condition, whatever the value of 0 it will pass towards the output, it will be good, or it can pass good logic 0. And when it is short circuited, it will pass the degraded logic 1. That means suppose 0 volt is a what we can say logic 0, and 5 volt is a logic 1. So because at its natural property of being normally off transistor, it can pass the good logic 0. That means whatever the 0 volt, it will not pass anything, right, other than 0. But when it acts as a short circuit, when it acts as a short circuit, it will pass a degraded a high voltage towards the output. That means point to remember is NMOS transistor, right? NMOS is able to pass good logic 0 but degraded logic 1, and reverse is the case with this PMOS. PMOS is capable to pass a good logic 1 and degraded logic 0, as it is naturally referred as normally on transistor, right? It is naturally referred as normally on transistor. म्हणजे इन अ व्हेरी सिंपल लँग्वेज एवढं लक्षात घ्या की एनमॉस ट्रान्झिस्टर हा नॉर्मली ऑफ म्हणतो. म्हणजे काय की तो जेव्हा शॉर्ट सर्किट असतो तेव्हा तो इट विल नॉट पास अ what we can say anything towards the output from the input. That's why it can pass a strong logic 0 but weak logic 1 for the NMOS, and for the PMOS it can pass the strong logic 1 and degraded or weak logic 0, as it is a normally on transistor. Okay, now coming to the CMOS inverter. Now what is the construction of CMOS inverter? Now if you connect the PMOS, right, this is a symbol of PMOS transistor and this is a symbol of NMOS transistor. Now if you connect the PMOS and NMOS series with each other, PMOS and NMOS series with each other, where PMOS is at the upper side and NMOS is at the lower side. Now that particular and if you short the gate terminals of this PMOS and NMOS, or you can connect it together, right? So this particular combination is called as CMOS inverter. जेव्हा तुम्ही PMOS आणि NMOS ट्रान्झिस्टर एकमेकांशी सिरीज कनेक्ट करता आणि त्यांचे गेट टर्मिनल्स एकमेकांना शॉर्ट करता, तर ते जे कॉम्बिनेशन असतं त्याला म्हणतात CMOS इन्व्हर्टर, right? So when you look at the circuit, now if you give 0 input at this point, what output you will get? See, input is 0. That means what? This 0 will go here and it will turn on this PMOS transistor and it will turn off this NMOS transistor. Now as the PMOS transistor, this PMOS transistor, right? This PMOS transistor is capable to pass logic 1, right? Strong logic 1, it will pass this strong logic 1 towards the output, right? हे VDD ला कनेक्ट आहे म्हणजे काय, तुम्हाला हे प्लस व्होल्टेज इकडं मिळणार आहे. दिस इज फॉर द एज इक्वल टू 0. इन्व्हर्टर केस म्हणजे इनपुट काय दिले तुम्ही 0, आउटपुट काय मिळालं 1, right? Similarly, in case of this in another case where input is 1, now see, input is 1, now this 1 will go here, this NMOS will be this PMOS will be off, and now this NMOS will turn on. This NMOS will turn on and it will capable of passing logic 0, right? So, and of course as this is connected to the ground, you will get the 0. Now why we have connected these two ट्रान्झिस्टर्स, बरोबर आहे? आपल्याला हे PMOS किंवा NMOS ने पण सहज शक्य आहे, बरोबर? मग हे दोन का वापरले? त्याचं कारण असं आहे, कारण PMOS ची कॅपॅबिलिटी काय आहे? स्ट्रॉंग लॉजिक 1 पास करायची, पण तो लॉजिक 0 पास करू शकतो का? नो, इट विल पास लॉजिक वीक लॉजिक 0, राईट? ही PMOS ची कॅपॅबिलिटी. त्यामुळे आपण PMOS चा जी स्ट्रॉंग लॉजिक 1 पास करण्याची जी कॅपॅबिलिटी आहे ती आपण इथं युटिलाइज केली. आणि एनमॉस कशासाठी वापरला? एनमॉस ची प्रॉपर्टी काय आहे की तो स्ट्रॉंग लॉजिक 0 पास करतो, पण त्याला स्ट्रॉंग लॉजिक 1 पास करता येत नाही, राईट? सो एनमॉस मुळे आता आपण स्ट्रॉंग लॉजिक 0 पास करतोय आणि पीमॉस मुळे स्ट्रॉंग लॉजिक 1 पास करतोय. दॅट मीन्स व्हॉट? द ड्रॉबॅक्स ऑफ ईच अदर बाय connecting in series with each other, we have compensated, and now we are getting strong logic 1 as well as strong logic 0, right? Strong logic 1 is passed by PMOS and strong logic 0 is passed by NMOS. म्हणजे काय, तर दोघांचे जे ड्रॉबॅक्स आहेत ते दोघांना एकत्र आणून आपण कॉम्पेन्सेट केले, आणि आता आपल्याला काय मिळते? आपल्याला स्ट्रॉंग लॉजिक 1 पण व्यवस्थित मिळते आणि स्ट्रॉंग लॉजिक 0 पण व्यवस्थित मिळते, right? This is what the CMOS inverter, right? Now, what is the concept of pull up and pull down network? Okay, so whatever the upper part, that is PMOS part, it is act as a pull up network. Why it is pull up network? Because when the NMOS is off, right? For example, when you give zero input, right, in that case only PMOS will be in the conduction and NMOS will be off. That means PMOS is short circuited, NMOS is open circuited. So this PMOS as is connected to the plus VDD, that means positive supply, it will pass this positive supply towards the output, and that's why this is called as pull up network, right? This is called as pull up network. So in CMOS, logic gates are collection of NMOS is arranged in a pull down network between the output and the low voltage power supply, and this PMOS is arranged between the high voltage, right? That means plus VDD and the output, right? So this upper network it as a pull up network, and this downward is act as a pull down network, right? So this is how you can use or this CMOS inverter can be worked in a pull up and pull down network fashion, right? Next point of this unit is a static and dynamic behavior of CMOS transistor, right? Static and dynamic behavior of CMOS transistor. Now, what are the static behavior? That means this static behavior is nothing. This static behavior is nothing but the uh, what you can say, the calculation of robustness, right? The static behavior is nothing but the calculation of robustness of CMOS inverter. And why we are studying the dynamic behavior? This dynamic behavior we are studying, that is because of to check or to analyze the performance of a CMOS inverter. That means how robust CMOS inverter, the static behavior analysis will tells us. And what is performance of CMOS behavior? To check this, you have to carry the, or you have to study the dynamic behavior of CMOS inverter. Now in static behavior, what are the different parameters, or what are different points that you should check? First, you should check the VTC. What is VTC? Voltage transfer curve, switching threshold, and noise margin, right? So these three parameters or these 3 points together will be analyzed for as a static behavior to check the robustness of CMOS inverter. How to measure or how to analyze the dynamic behavior, right? So that it performance can be estimated. To calculate or to analyze the dynamic behavior, you have to first study the different capacitances and delays, right? So this is the static and dynamic behavior. Now first we will study the static behavior of CMOS inverter. In that, first is a VTC, that is voltage transfer characteristics. Now as you know, this is the voltage or VI characteristics of CMOS inverter, right? This is the or it is a voltage transfer curve. It is a out in uh, output voltage. This is the input voltage, right? Input output relationship. So as you study, this is the response, right? For this is the response of CMOS inverter. So in this first region, right? In this first region, the PMOS is off. PMOS will in a linear region and NMOS will be off. That means in a cutoff region. At this second point, right? At this second point, the NMOS is in a saturation, PMOS is in a linear region. As this curve is having the 5 different region of characteristics, right? Now in the third region, that means in this region, this particular region, NMOS is also in saturation and PMOS is also in saturation. At this region, the NMOS is in the linear or ohmic region, PMOS is in the saturation region, and at this region, NMOS is in linear region and PMOS is a cutoff. PMOS in a cutoff region. So this is how this different operating conditions for the uh, CMOS inverter can be studied, right? So there are actually five region of operation, right? Depending upon this input output characteristics. So in first region, NMOS is off, PMOS is in linear region. In a second region, NMOS is in saturation, PMOS is in linear region. In a third, PMOS is in saturation. Also, NMOS is in saturation for this third region. Coming towards the fourth region, NMOS in linear and PMOS in a saturation region. And in a fifth region, NMOS in linear and PMOS in cutoff region, right? So these are the different operating conditions or voltage transfer characteristics of CMOS inverters. So you have to study this. Now, what is this? What is second and very important point that you should consider to analyze the static behavior is the inverter switching threshold. Okay, what is this inverter switching threshold? So this is not your VTH, right? This is not your VTH of the device. See, as you know, if you consider NMOS or PMOS, doesn't matter. It has a threshold voltage, but this switching threshold is nothing to do with that device threshold. Now, what is this? So basically, it's a midpoint, right? So it's a midpoint of the threshold of this NMOS as well as PMOS, right? Where this V out is equal to V in, right? If you plot a graph so that the V out is equal to V in, the midpoint of this, that means what? There is a 50% part for the 50% part above that graph and 50% part below that graph. And midpoint of this is nothing but the switching threshold, right? This is a point where this V in is exactly equal to V out. That means a very middle portion of this linear line. This is called as switching threshold, right? This is called as switching threshold. Now this VTC is symmetric as this will improve the noise margin, right? When if you check the symmetry of this middle line or this linear line, you can find the exact symmetry, right? You can find the exact symmetry. What it means? The noise margin is improved. Noise margin is improved, right? And this particular point of observation is called as switching threshold value of CMOS inverter. The third point that we should study to analyze the static behavior of CMOS inverter is noise margin. Now, what is noise margin? Right? What is noise margin? So first we have to understand the definition of this noise margin. So noise margin is the amount of noise that a CMOS circuit could withstand without compromising the operation of circuit, right? What is noise margin? Noise margin is the amount of noise that a CMOS circuit could withstand without compromising the operation of circuit. That means what? The amount of noise that you can add to that particular circuit, but it will not get affected on that circuit, right? So that particular margin is known as noise margin, right? Means what? Noise margin does not make sure that any signal which is logic 1, for example, right, which is logic 1 with finite noise added to it is still recognized as logic 1 and not logic 0. म्हणजे काय की अमाऊंट ऑफ नॉइज की एखाद्या सिग्नल मध्ये तुम्ही किती नॉइज ऍड करू शकता की त्या सिग्नलच्या प्रॉपर्टीज काहीही फरक पडणार नाही, तर त्याला म्हणतात नॉइज मार्जिन, right? त्याला म्हणतात noise margin. Now how to calculate this noise margin? So basically it is a difference, between the high noise margin and low noise margin. Now how to calculate this high noise margin? It is a VOH, minus VIH. Where is VOH? Here. It is a VOH minus VIH, right? This one. And low noise margin is nothing but VIH. That means this VIH minus VOL, right? VIH minus VOL. Difference between VOH and VIL is the high noise margin, and difference between the VIL and VOL is the low noise margin. And difference between this NMH and NML is nothing but the noise margin. And difference between this NMH and NML is nothing but the noise margin, right? And greater the noise margin, greater the noise immunity of that particular device. जेवढं noise margin चांगलं तेवढं त्या deviceची what you can say noise immunity आपण ज्याला म्हणू ती चांगली असते, right? So this is about the static behavior of CMOS inverter. Now we will talk about the dynamic behavior of CMOS inverter, right? Now what is this dynamic behavior of CMOS inverter? So first you have to study the capacitances, right? So you can see on this screen, there are certain parasitic or intrinsic and extrinsic capacitances that are that lies with the MOS transistor, right? So this is a capacitance between source and gate, right? This is a gate terminal, this is source, this is drain, and this is a bulk, right? So capacitor between the gate and source is known as CGS. Capacitor between gate and drain, it is known as CGD. Capacitor between the source and bulk, it is known as source to bulk capacitance, that means CSB. Capacitor between the drain and bulk, it is known as CDB. And capacitance between the gate and bulk is known as CGB, right? Now this CGB or CGB is equal to GCB, right? GCB. This CGD is nothing but GDC, right? Plus GDO. That means this gate to source, gate to drain capacitance, right? And plus gate to drain capacitance for open circuit and short circuit, that is closed circuit, right? So basically these six capacitance, basically these are the actually extrinsic capacitance of the MOS transistor, and along with this some wire capacitance or metal oxide capacitance, gate oxide capacitance, these are the intrinsic capacitance of this MOS transistor. Now with this, if you continue about the inverter cascade capacitance. Okay, we have studied about a single MOS device. Fine, that is well. For the single MOS device, these are the different capacitance. But what happens, right, when there are two different CMOS inverters are cascaded, that means connected in series or maybe a parallel, then how many capacitance will be contribute in this inverter cascade capacitance? So it's a CGD1 and 2. That means this CGD1 and this CGD2, right? Gate to drain capacitance. It is observed at the drain of driving inverter output. It will affect the output, right? Now this CGS3, CGD3, 4 and CB3 and 4. That means gate to source capacitance of this third and fourth, gate to drain capacitance of this 3 and 4, and gate to bulk capacitance of transistor 3 and 4. This total will contribute or will affect the input. That means as it is known as gate of loading inverter, that means fan out capacitance, and it will affect the input of that particular uh, cascade inverter. And this is the wire capacitance CW. As we have connected this two cascade combination with each other with a wire, this CW, that means wire capacitance or this parasitic capacitance, is also contributed in this entire capacitance. Now why to consider these capacitances? Because these capacitances will able to help you to analyze the performance of that inverter, because these capacitances also with these capacitances itself lead to some sort of delays, right? Some sort of unwanted thing in the inverter, right? So while studying the dynamic behavior, first you have to consider this capacitances, and second one is the delays, right? Now, what do you mean by delay in any kind of CMOS or MOS transistor or inverter? So basically it's a propagation delay. Now, what is propagation delay? The propagation delay is the amount of time that it takes for a change in the input signal to produce change in the output signal. राईट. प्रपोगेशन डिले कशाला म्हणतात, की इनपुट सिग्नल मध्ये चेंज झाल्यावर तो किती वेळाने आउटपुट सिग्नल मध्ये रिफ्लेक्ट होतो, तो जो टाइम लागतो त्याला म्हणतात प्रपोगेशन डिले. त्याला म्हणतात प्रपोगेशन डिले. नाउ हाऊ टू कॅल्क्युलेट दिस टीपीडी? TPD stand for propagation delay. So TPD is equal to max of TPHL comma TPLH. What is this TPHL? High to low propagation time and low to high propagation time. म्हणजे high to low. Suppose इनपुट सिग्नल हायला गेला तर आउटपुट सिग्नल हायला जायला किती वेळ लागतो, हा झाला हाय टू किंवा इनपुट सिग्नल हाय टू लो ट्रान्झिट झाला तर आउटपुट सिग्नल हाय टू लो ट्रान्झिट व्हायला किती वेळ लागतोय, हा झाला हाय टू लो प्रपोगेशन टाइम. आणि ह्याच्याच उलट सपोज इनपुट सिग्नल लो टू हाय झाला तर आउटपुट सिग्नल लो टू हाय जायला किती वेळ लागतोय, हा झाला लो टू हाय प्रपोगेशन टाइम. आणि या दोन्हीतला मॅक्सिमम जो टाइम असेल त्याला तो टोटल प्रपोगेशन डिले ऑफ द that particular device. Max of this high to low or low to high will be the total propagation delay, that is TPD, right? And this TPD determines the gate speed, right? बरोबर आहे का नाही? इनपुट चेंज झाल्यावर जर का तासाना आउटपुट चेंज होत असेल त्याला काय उपयोग नाही. फास्ट रिस्पॉन्स पाहिजे. इनपुट चेंज झालं की लगेच ते आउटपुट मध्ये तुम्हाला दिसलं पाहिजे. बरोबर आहे का नाही? सो इट्स डिपेंड्स अपॉन द प्रपोगेशन डिले. Right? Now this next part of this unit is the power consumption analysis of the CMOS circuit. Okay, now this part we will cover in the next lecture. Okay, for today we will stop here. If you have any query or doubt, you can ask me right now.